here, and again this is there a pointer? Okay, it's okay. This NMR spectroscopy, Dr. Oh, anyway, on the screen it doesn't. Okay. Intensity is so low. Okay, anyway, we have good old stick. This NMR spectroscopy, I will not be talking too much, but I introduced to the topic and leave it for the tomorrow's session. Tomorrow, right? Tomorrow session, Dr. Shashi Kumar, he will be talking gymnastics associated with these spins. I will leave that field, and then I will concentrate more on what is the highlight of the solid state NMR. Of course, I will talk about NMR spectroscopy and tell what I am not going to talk. Okay, what is the room left for Dr. Shashi Kumar, and then I will concentrate on the relatively different field. It is not available readily the way you go through Google Amma or Google Uncle to search for that. That's not so available. That I will try to highlight that and what are the importance of that. And then I will be talking about what are the different materials we have studied in our lab and what is prominent topics or systems to be explored. Okay, and some of the whatever the documents or whatever the results I am showing it, they mainly concentrate on some of the papers which are presented over there. Some of our research I have not included much. What I am going to do, depending on the time. What is the time now? How much time I will be allowed right now? 1:15. That 1 hour. Please remind me 10 minutes before. Since I have other session also, it will be continuation of that. Okay. Hence, I can always stop at any point. I don't delay your lunch. Okay. I'll take it up from there and we'll continue in the next session. And then some of the results I will be showing it to you today. And this entire work again spanned around all these different cities, including University of Arizona, IISc, Bangalore University, and right now Ramaiah University. Basically, we know that we always get started with that. This is my favorite slide. All of us are familiar with this electromagnetic radiation. Why should we care about that? As we know that in layman's language, this electromagnetic entire spectrum spans from radio waves which are having very, very low energy. That's why every day we are getting exposed to that. So far, just present human mankind or nobody is getting affected too much. Hence, we are extensively using that part of the electromagnetic spectrum for all our communication purposes. And then it goes into the other end of that is very high energetic rays, X-rays, and beyond that gamma rays. And again, gamma rays also we use it whenever our human cells are not working well, cancer cells and other things. Whenever we want to kill that, we use the other part of the electromagnetic spectrum. Therefore, it is bread and butter for all of us, mostly for the spectroscopist. This is the bread and butter for all of us, and even for the general mankind. Radio waves, as you know, that it is used for the communication purpose. And again, all of you, whenever you go to bakery, when you ask him to give samosa, all of you would have seen that hot samosa he will give. How does he heat up samosa? Have you experienced that outer layer of the samosa? Is it with the same hotness like that of the whatever the inside some what is that aloo based stuff? Have you seen that difference between those two temperatures? Okay, I literally broke one of my teeth when I chewed that. Okay, that potato stuffing. Okay, why does it happen over there? Why outer surface is not heated up to the same extent of the inner? All of you know that, right? Water molecule. Okay, that is the microwave reason. Okay, it can only is a selective heater. Okay, that can only perturb the vibrations associated with the aloo or water content present in that. Hence, it has enormous applications associated with that. And then we have that infrared rays, that the way Whenever I press this button, it is coming back. Okay, I'm using the IR rays to connect to all my remotes, TV remotes, everything is associated with that, and also IR cameras. There are many more. Let us not spend too much time just to know that nothing different we are talking about. What is known thing only in one reason, we'll narrow it down. And then we are having visible light. That's how you are seeing me, and I am seeing all of you. Without that scattering of light, we would not have seen. And then we have ultraviolet rays. Again, whenever we want to protect, we always go for the UV goggles to protect our eyes whenever that is little harmful. That's why we label this is our boundary line. To the left of this, we call it as non-ionizing radiations. Right of that, we call them as ionizing radiations. Then we start caring much here. Ultraviolet rays and then X-rays, all of you know that is our bread and butter as a physicist. Okay, we use a different range, and gamma rays, as you know that whenever we have to kill really somebody, some heavy microorganisms, okay, we use that one. Okay, with that background, and whenever we look at the energy levels associated with that, we can see that radio waves will be having frequencies of the order of 10 to the power of 4 hertz, okay, and that goes up to 10 to the power of 22 hertz. Okay, it spans around 20 order of magnitude. It changes from one end to the other end, hence it allows us to use them for different applications. As a spectroscopist, whenever we look at that, or when we look at that from the molecular spectroscopy point of view, lot of these radiations, that is for the previous slide is for dummies, this is for the real spectroscopists. Okay, as you can see at this point, okay, all of you have seen there are different reasons, and we give different names for the interaction of this electromagnetic radiation with matter with different subheadings. Okay, let us look at these subheadings from this diagram here. Okay, this is radio waves and microwaves. Whenever that same electromagnetic radiation interacts with the nuclei present in the atom, we call it as nuclear magnetic resonance. And then whenever the electron, the spin property of the electrons and neutrons or nucleons, we call them as NMR, correspondingly ESR. And then whenever molecule is undergoing rotation or vibration, then infrared region, whenever we make it to incident on the light ray or on a given system, then molecule starts rotating. And again, if I increase little more little more extra near infrared region, again I can make my molecule to vibrate, or through this interaction I can recognize what kind of rotation is happening in the system as well as what kind of vibration is happening in the system. I can detect it. Spectroscopist major topic is I want to recognize what is happening in the given system. By using this spectroscopic technique, I can measure the vibrational energy levels, rotational energy levels, how it is changing with respect to whatever the doping, as Dr. Biswas, Raju Kumar Biswas was talking about the doping. How do you characterize different materials? What is the effect of doping? If I want to characterize it or categorize it efficiently, I go with this spectroscopy technique, and then I know that definitely this material is present in the system. And again, our next system is spin reversal. Basically, whenever I am playing with the spin of the nucleons or electron alone, okay, that type of interaction of this electromagnetic radiation with that would help us to alter the equilibrium states of this electron spin state and nucleon spin state. That we call it as NMR and ESR. And as you know that whenever we play around with the innermost electrons of the system, that is the X-ray interaction, X-ray fluorescence, there are many techniques associated with that. And then whenever we are having about the rearrangement of the nuclear particles, that can be leading to the gamma rays, and there are potential applications. In my talk, what I am going to concentrate today is only restricted to this part of the electromagnetic spectrum. And here, what is NMR? NMR means nuclear magnetic resonance, as you all of us aware of the fact that resonance means there should be a match of two things. Okay, here I am going to talk about how magnetic moment associated with nucleons would interact with the external radiation and how one can change the state of the system. Okay, whenever we achieve that, we call it as a nuclear magnetic resonance. Whenever we record the spectrum out of that interaction, that we call it as NMR spectrum or NMR spectroscopy. And how does it really happen? All of us know that our nucleus is consisting of protons and neutrons. Sorry, I'll just quickly go through it. I will pass it on the rest of the information to Dr. Shashikumar for tomorrow. I'll come back to point. The basic fundamental rule over here is our nucleus consisting of nucleons, that is protons and neutrons, though they do not, in the sense neutrons do not possess charge, but they do have spin system, or they do behave like a tiny magnets. And the only thing is these tiny magnets, they always keep rotating or keep directing towards different directions. They are randomly oriented. The net effect is zero. What we can see that, but we'll come back to that fundamental question at the later stage. And then whenever these magnetic moments, they behave like tiny magnets, but whenever they are directing towards different directions, but at that point if I apply magnetic field to that system, then the person, whenever I am not standing here, all of you would have been looking at different directions, the net effect would be zero. But when somebody is standing over there, this is the magnetic field being applied to you, then all of you start looking at me. Like that, whenever we apply external magnetic field, they start, the net magnetization orients along the direction of the magnetic field, and then they start precessing around that. It purely depends on the strength of the magnetic field. What is the frequency at which they start precessing around the static magnetic field? It purely depends on that. At that point, okay, whenever I apply magnetic field, all of you start looking at that, then I will shine external radiation and make you to move or make you to direct in the opposite direction. I can always change your orientation from one direction to other direction. Then I am causing the transition to occur. That resonance condition at which exactly I can change your orientation from you're pointing towards me, I can make you to go in the opposite way. We call it as resonance condition. That's what we call it as nuclear Zeeman effect. Once nuclear Zeeman effect is set, then during the application of magnetic field, all of them start aligning in one particular direction, and corresponding mathematical equation, I'll show it in the next slide. Okay, basically at nutshell, whenever we apply electromagnetic radiation to that kind of a system, then I can change their energy, your orientation from one direction to the other direction. Okay, and whenever you change your orientation, I can detect your orientational change. That change is recorded as a spectrum, that we call it as nuclear magnetic spectrum. Okay, I think all of you have studied the same thing as part of the curriculum. Okay, and if that is the case, this question I may not address it immediately, I'll address it at the later stage. And if that is the case, all atoms do contain nucleons, that is protons and neutrons, then can I have this nuclear Zeeman effect and NMR signal can I observe from all the nuclei? What is have you already studied this topic? Have you studied? How much you remember? Yes or no? So that should guide me how much I have to spend my time right now. Huh? Okay? Yes or no? Whenever I am asking yes or no, obviously there should be no. Otherwise, I would not have put the question. Is it not? Obviously, right? Common sense. Whenever you have to take just and other GATE exams, your first job is to rule out what are the wrong answers. Okay, then think about what are the possible answers. Then search for the best answer out of that. Okay, you should have that presence of mind at that point. You have to adapt. Okay, because at that point, within 1 minute, you cannot work out the entire equation to get the final answer to check whether it's correct or not. All of you agree with me? Yes, right? Same thing. Here they do not. I will talk about that why they are not. Basically, what we are going to do is that whenever I apply external magnetic field here, when magnetic field is zero, only one energy level will be there. For example, whenever I am having hydrogen atom, okay, hydrogen atom is having how many neutrons and how many protons? Only one proton, okay, it is a spin-off nucleus. Okay, hence its spin quantum number is off. Okay, whenever I apply external magnetic field, okay, depending on the strength of the magnetic field, that one half splits into plus half and minus half either sides, and then it becomes two energy level system. Whenever it is having the two energy level system, the gap between these two energy levels is directly proportional to this delta E is directly proportional to B naught, the strength of the external magnetic field, and it also depends on what nuclei I am considering here, gamma. What is the name of the, what is gamma? Gyromagnetic ratio. Okay, the correct explanation or symbolically it is magnetogyric ratio, the correct word. Okay, it is the ratio of the magnetic moment. Okay, and this value will be varying or will be different for different nucleus, okay, or different atoms. Okay, hence the gap between two energy levels will be different for different systems, though the spin quantum number can be same. Okay, your spin quantum number can be same, but gamma could be different. Hence, we get different magnetic field to be applied to observe NMR spectrum for the same sample. Or the other way, I can say that though my applied magnetic field strength is same, depending on different gamma, different atoms present in the given molecule what I am studying, I will get different NMR spectrum. That would enable us to identify what are the atoms present and how they are oriented. That is the deeper level understanding. Fundamental rule is, since gamma decides the energy gap, okay, and it depends on the static magnetic field, and the same, this is the classical picture. Whenever they are oriented, if they are spinning around the static magnetic field with what frequency, that is decided by this nu, that depends on strength of the magnetic field. This is a classical picture. And whenever I shine electromagnetic radiation, so that exact h nu, whenever I supply through irradiating the radiation, I can make these systems to change their orientation, then net magnetization gets into the other position. That we call it as, instead of spinning in this way, they go back and spin in the opposite direction. That's what we call it as anti-parallel. Okay, anti-parallel Larmor frequency. With the same frequency, they start spinning in the opposite direction. Whenever they go from this direction to this direction, how much energy is required is decided by this B naught value. Is it clear? All of us got the point, right? And exactly how do we measure it? If all of you are directing towards me and immediately one more person comes in the back and all of you turn it in the other direction, how do I measure it? For that, what we do, since whatever the radiation required to make this transition to occur, it is in the radio frequency region of the electromagnetic spectrum, I can always take your synthesizer, signal generator. All of you could always change the frequency, right? The signal generator, you have done LCR experiment, LCR resonance experiment. You change the frequency at one point, it gives LCR series, LCR connection. Capacitor and inductor were connected in series, it gives maximum current at one frequency. From that, you measure the Larmor frequency. Same way, I will do that. I don't use any other radiation to shine electromagnetic radiation. Electronically, I send electromagnetic radiation to pass through it. What we are going to do in this particular case is, I will take one inductor, okay, I will make a coil, and within that coil, you assume that this is the sample tube. I have filled my sample in this. I have an inductor. That inductor is connected to the rest of the circuit, and I have kept this entire sample tube inside the magnetic field. For example, this is a superconducting magnet. I keep my sample in this direction or different directions, it doesn't matter. Okay, depending on our interest. Okay, only thing is that here magnetic field is in this direction, and whatever the direction it induces should be perpendicular to the direction of the static magnetic field. That's the only condition what we need to pay attention. At that point, what I am going to do, once I keep my sample tube inside the coil, and this energy levels got separated, and at that point I send radio frequency signal through this coil. Whenever that applied radio frequency signal exactly matches with that of the energy gap, immediately current detection in the circuit, okay, little absorption happens, they absorb the energy, immediately current flowing through the circuit changes. The way he did the first derivative of the, if it is a flat, your derivative is 0. Whenever there is a kink, I can immediately see that at what point kink is coming up. That kink gives that exactly at what frequency I observe the NMR signal. Basically, same thing would have been taught in your regular class also. I can do the same experiment, or I can do the other experiment. I fix my frequency constant. Okay, I keep on changing the magnetic field. Okay, I will apply to whatever the 10 megahertz with my signal generator. I keep on adjusting the current flowing through the electromagnet. At that point, immediately it absorbs the energy. That also, I only need change in the orientation. Like that, I detect the signal. Usually, the detected signal, we record it in terms of free induction decay. This one, if I get time, I'll get back to the finer details of that. There are two ways to measure this NMR signal. Okay, this FID corresponding to, instead of sending radio frequency continuously, I can always send it through small short pulses of 10 microsecond only. I will shine the light at a time and I can get that signal. That time that induces current in this inductor, okay, that we call it as free induction decay signal. Okay, if it's required, I'll get back to that, but this much information is very much essential for me. And then you can think that why this NMR is so useful, or why are we worrying too much on that. This NMR can be used for many applications. Okay, and probably Dr. Shashikumar might tell about the history of that, why, how many Nobel Prizes got in this particular field. Okay, how it is able to detect whatever the problems which are happening in our system. All of you have heard about MRI, right? Magnetic resonance imaging. Okay, that is the realistic application of this NMR. Okay, and since why we are going with this technique, X-rays means they are highly energetic radiation. Whenever they pass through that, they can damage soft tissues. But these are all radio frequency reason. The frequency is very less than that of the light. Okay, they do not perturb much. I can always use this technique for brain related studies whenever something is happened. Okay, MRI, is it a diagnosing tool or a what is that? Is it only used for diagnosation purpose or curing purpose? MRI. It is purely to diagnose where is the problem, to identify only we are using it. It cannot cure it, but only at the other cases we can use it, not in a regular way. Like that, that is one particular technique if you have to consider. Okay, and that's what we call it as functional imaging, and in hospital we are using it, and the same thing for the medicine purpose. Again, if I want to know the concentration of particular seed or concentration of oil in your coconut, sorry, groundnut, okay, I can always use that. Wherever we have more concentration of given fat content, I can always detect that that particular concentration is more. Okay, that is more healthier food. Okay, and in soil sciences, if I want to study some of the special properties of the soil, okay, one of our field papers are on the soil sciences. I will not get into that. The major one, let us concentrate on the physics part of that. Okay, whenever I want to measure that, whatever the doping morning we did it, okay, whether exactly 0.1% Dr. Our uh, Vishwas, uh, when he was talking about the doping concentration, exactly how much you added. If I want to calculate, I have to go with this technique to identify that yes, you added only 1 gram of that and 2 grams of another material. That's what we call it as structural composition. Okay, composition of the molecule, atoms, different atoms. If I want to measure it, I can go with this physics part. And in forensic science, okay, again similar behavior. I am not getting into more details over there, especially the structural chemistry. Okay, most whenever I talk about the NMR, so solution state NMR for all organic chemistry or inorganic chemistry, guys, this is the bread and butter for them. The way those who are working in the research area, for us, the XRD pattern is the must characterization technique. Like that, for all chemistry guys, it is NMR is the first and foremost technique. Whether your molecule has formed or not, they identify with that, and from that, because as I told you in the initial time, the different atoms are having different magnetogenic ratio, gamma value. They give peaks at different magnetic field. That they try to convert it back into some other unit, and they can identify different functional groups associated with that. And in the material science, this is where I will be spending much time today over there, how this same NMR can be utilized. Hence, it has wide applications in most of the fields. Okay. Now, let us try to understand what different types of, when, as I told you in the previous one, once atoms get excited from one energy level to other energy level, okay, there are two types of relaxations through which they come back to their ground state. One is spin relaxation time, other one is spin lattice relaxation time. Okay, it's a, what you need to know is that whenever atoms go from lower energy level to higher energy level, how much time they take to just spread over in their excited state, that we call it a spin relaxation time. And how much time they take to come back once I make them to go up, how much time they take to come down, how much time they take, we call a spin lattice relaxation time. These are the relaxation mechanisms through which I can study many parameters. Okay, by studying this, not only the structure of the molecule, also dynamics associated with the molecule can be studied with these techniques, and details will be discussed in the tomorrow's class. These are the experimental methods how to calculate those relaxation times. Okay, I'll not get into that. This is the typical solution state NMR. Here we are having the sample tube. We drop it from the top and it comes at the center, and I'll send the radio frequency to this inductor, and then whatever the induced EMF will be collected back and displayed as a NMR signal. Okay, and as you can see that this is one of the proton NMR signal. Okay, I'll leave all these things to tomorrow's class. Okay, what I need to emphasize for today is that by studying the chemical shift, that is one of the parameters through which I can distinguish different functional groups. As you can see that although my gamma is same, I am doing only proton NMR. Okay, that means hydrogen NMR. Gamma is same, but they are at different localized environment. CH3 group is having 3 hydrogens connected to carbon. CH2 group is having only 2 hydrogen atoms connected to carbon atom. If I take the benzene ring, again it is in a aromatic ring. Their chemical environment is different. That chemical environment makes them to resonate at different positions. And once I record the NMR spectrum, I will get for CH3 molecule at particular chemical shift, I will get spectrum over there for CH2 group, OH group, and when you come back to the right hand side, so many other functional groups, ketones, aldehydes. Okay, we get different positions. That's why, as I told you in the beginning, at nutshell, for an organic chemist or anybody, they fundamentally is whether this ketone is formed, hydroxyl group is there or not, they do go for this NMR spectrum first. once they synthesize in the compound. From that, they try to interpret the what is the other fundamental functional details associated with that. That itself is an independent topic, and this is one of the first. This is the first one. Or it's whenever we take ethyl alcohol, okay, we are expecting only hydrogen is present, hydrogen NMR. We are expecting only one peak to appear. But what has happened when we record it, we got 3 peaks instead of one peak. That 3 peaks corresponding to wherever we are having 3 hydrogen atoms, okay, that intensity of the signal is very high. And whenever we are having only 2 hydrogen atoms, intensity is relatively less. And another one is only hydroxyl group, OH group, 1 hydrogen is there, we got the signal strength like that. But why they are appearing at different positions? Because how much these hydrogen, whatever the neighboring shielding of the magnetic field happens at that individual point, probably that I'll not get into much of those details. I'll skip over there. What you need to know is that different functional groups give signal at different positions for the same nucleus. Okay, obviously it is obvious that whenever I change the nucleus, their entire spectrum will be different. That's why whenever you go and give your sample for any NMR facility, the first thing they will ask that what NMR you want to do. Whether you want to do hydrogen NMR, carbon NMR, nitrogen NMR. Okay, that much you should be aware of that, why you are doing it. Yes. Ah, 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 if I have to talk about that, see, just to compare it, by default, whenever they did this experiment at low resolution, whenever the strength of the magnetic field is very less, they got only one peak. But when we go to high magnetic field, okay, I am able to resolve several peaks which are under this. Okay, then CH3 peak itself got split into 3. There is a famous table. That's why I'm not getting into more details associated with that. Electronegativity in that particular paramagnetic impurity is added up in certain systems. Okay, it can shift, but generally whenever we do, that's where they try to first they get it whether the any impurity is present or not. They immediately get to know that if they are not getting any of the peaks at this region, okay, they rule out that to prepare once again. Let us cross check that. These are all diamagnetic samples. We'll come back to that. Ferromagnetic compound, that's my first area. We're going to talk about that. Since it is a general one, whatever, as I told you that Google uncle can give you, this is the standard one. Most of the people use this, not the conventional NMR we call it. Okay, we are already, I will not get into more details of that. That chemical shift will be evaluated based on the what is the electronegativity associated with each group of the proton. Okay, and then with this method, people can identify or predict the structure of a given 100 kilodalton, whatever the size of the protein molecule, they can identify the secondary structure, tertiary structure. Okay, that's why biologists and chemists use it regularly and much more efficiently. That made this NMR spectroscopy to be so dominating technique. So many Nobel prizes were awarded for that. Initially, 3 people predicted that, and also as I told you, I think he will talk about that just for the spin relaxation time. Whenever you get started with the new experiment, by default, if you would have taken a sample which is having high relaxation time, it takes 1 day to come back. Whatever you do today, experiment, it won't come back. Oh, I am not getting the signal, I am not getting the signal. That literally happened when they discovered this technique. Initially, 2 groups were parallelly working on that. Okay, 20 days. Just giving an example, it can go from one end to the other end. Okay, we should be aware of that particular factor. Okay, this is broad introduction, and based on that, your application, it has been characterized into solution state NMR, solid state NMR, and MRI imaging for the biologist imaging purpose. And here, basically, the aim of the solution state NMR is to predict the structure, that is the dominating factor. What is the experimental parameter is chemical shift. What is the chemical shift for individual peak, they identify, and that's the end of the story for most of them. Next one is solid state NMR. Along with the structure with solid state NMR, I can also measure the dynamics. That's what I always give a standard example. Your X-ray, whenever you take the X-ray, take the static picture. Okay, what is the composition associated with that? With this NMR, not only looking at me, you are looking at what are all the motions happening whenever I am moving around or talking. Okay, what is the movement of my hand, movement of my lip? Okay, what is my physical location? All of them are at different time scales, right? You can visualize that all those things can be captured by measuring the NMR spectrum and by measuring the relaxation times associated with that. Hence, that is more essential for our physicists. Hence, not only the chemical shift, relaxation rates, we measure it, and then we measure it as a function of different frequency. That gives you spectral density analysis, makes us to measure much or analyze much of the physics problems. The last one is in MRI technique, they inject one ferromagnetic impurity and they identify how relaxation is modified within the small region. From that, I can extract what is the bad cell happening in the given region of the human body. From that, it is not happening the way it was expected. Hence, there is a problem. Like that, it identifies, and you could see that this is the energy with which we I am sending the radiation is of very, very, very low energy. Hence, even whenever pregnant women can also undergo this treatment. All our brain MRI scanning, mostly people use it for brain, right? Because it is more expensive compared to your X-ray. Okay, hence whenever it is essential, then only they go for this. Okay, and soft tissues can be effectively studied. Okay, and since whenever we are talking about material science and the biophysical chemist, then we concentrate more on solid state physics. And here, the simple answer to my earlier question is whenever we are having these kinds of atoms, okay, a nucleus with even mass number and even charge, their spin quantum number is I is 0. When I is 0, it cannot interact with the external magnetic field, hence I cannot measure the NMR signal. For carbon 12, oxygen, sulfur, I can measure the NMR of proton or carbon 13. Please remember, carbon 12 cannot be measured, carbon 13 can be measured. Okay, again, nitrogen 14 is different. It is having different spin quantum number compared to nitrogen 15, and phosphorus, you can measure them. Okay, only few nuclei one can measure using this technique. It is an advantage for us also at many places. Talk about the advantages of that. Okay, and then this is what we have studied so far, or what is well known to us for several decades. There is one more technique called internal field NMR. As I told you that whenever I want to change the spin energy level from spin of one state to two states, I need to apply magnetic field. Zeeman effect comes into picture and splits the degeneracy. But there are certain nuclei, their internal magnetic field itself is so high, okay, that is enough to split the degeneracy. And again, I can do the same kind of studies, whatever I discussed over there. Okay, the only concern over there is only few materials or few elements can be studied using that technique, that we call it as internal field NMR. The beauty of that is the major expense what we get it for your MRI scanning or any of the solution state or solid state, different type of solid state NMR, is that how much money I have to pay for superconducting magnet. All of us know that superconductor means I need to cool down the material. to that much low temperature, helium temperature, nitrogen temperature minimum. Okay, that enhances the cost of the operation, or the spectrometer tile. Okay, costs us more. That can be avoided using this internal field NMR. Here, what we study is that the material should be ferromagnetic material or antiferromagnetic material or ferrimagnetic samples, what we require. And here, the relaxation, whatever the condition remains same. Here, only thing is this internal magnetic field will be different for different type of nucleus. Iron is 57. Huh? Internal field in next slide I have all of them. Okay, this iron, it comes around 57, 71 megahertz corresponding to that. Okay, and cobalt, manganese and nickel, only these can be studied, not all the samples. Okay, that is the only restriction for this particular technique. Okay, and this is why people go, as I told you, that one peak got separated into several peaks. That sensitivity of the NMR signal detection can be changed from, you can also see the numbers, how it goes up. Whenever I want high resolution spectra, okay, billions, millions, it gets into that. Okay, that's why it is more difficult, or also it is hard to maintain this kind of high level NMR spectrometer. That's why only one or two we get it in a city or in major towns. Okay, and here whenever we apply 1 Tesla magnetic field, your hydrogens will resonate at 42 megahertz. Whenever I apply 42 megahertz in your signal generator, okay, I can detect the NMR signal. Whenever I am applying 1 Tesla magnetic, what is the equivalent magnetic field value in terms of gas for 1 Tesla? 1 Tesla corresponds to how much? 10,000. Okay, 10 power 4 gas. Okay, what is the earth magnetic field? 42.5 micro Tesla. Okay, hence sometimes that zero field NMR, okay, it is internal field NMR. In some textbooks they also call it as zero field NMR. Okay, that one we cannot avoid it, that will be there always. Okay, now what I am going to talk about it is today morning he talked more on materials perspective, but in my case by same materials in terms of biological importance I will talk little bit. Okay, I will touch upon the material science as well as that internal field what I talked about it. Okay, most of my recent work is on this. This work is mostly during my PhD period. Okay, and this work is during my postdoc period at University of Arizona. Okay, always we take that America first. Okay, we take that biological samples first because they are little different from conventional way. Why as a physicist we should care about that? Okay, I'll talk about that biological systems. All of us know that our skin is it is made up of phospholipids. Okay, and either sides water is present, and this is the structure of the lipid bilayer membrane. Okay, and this basically the cellular membrane separate from one part of the human body to the other part. Okay, and they made up of these kinds of lipid molecules. Okay, they are of different chain. This is phospholipid, DMPC, dimethyl phospholipid. Like that we have depending on the different types of the head group and also the chain length. Okay, different types of lipid will be constituted in any human body or any other cell. Okay, I can study the properties associated with that with the same technique. Now that is to measure or to study the structure of this entire lipid molecule. The second one is whenever these kinds of lipids are, that entire skin is spread horizontally, then there are different types of motions associated with that. That entire lipid, that thin layer, okay, that can fluctuate in this particular way. Viscoelastic membrane deformation does happen over there, and there are molecular diffusion, that one lipid rotates this way and another lipid rotates this way. Okay, the dynamics are in the range of, can you see that it is in terms of microseconds, it will be in terms of milliseconds. And again the entire chain here, this fellow doesn't sit quite, CH3 wobbling happens. That motion occurs at much lesser time scale. That means to say frequency is high. 1 over t is frequency, right? Therefore frequency of oscillations of individual segments will be different. Here this will be different, and this one is also different. If I have to connect this experimental technique, the beauty of that is there are different techniques. One can measure all the dynamics associated with the lipid membranes like this. Is that okay? Some of those things, atomistic molecular dynamics simulation studies, people study. What we are going to do through NMR is that some of the studies we cannot do it independently. Okay, remote, some of the, if I want to understand in simple nutshell, if I have to put it, if I want to understand how drug is delivered to a particular cell in the human body, whenever we get headache, I take a pill, it directly goes, and immediately within half an hour or 1 hour I don't see that, right? How does it really happen? Whatever I take it through mouth, it has to go and dock to the particular cell which is causing the problem, and immediately that vanishes. How does it really go? Okay, during that drug discovery, I need to understand how this dynamics and structure is associated, and once I know the dynamics associated with that, from that I get the force fields associated with the different types of molecules over there. That gives the fundamental experimental validity for the molecular dynamics guys to predict whatever the functional changes happening in the given system. Okay, hence it, in a different way, it directly connects to the realistic application, that it is not so easy to do experiment. Hence all these motions, you can see that from this region to this region, from this region to this region, by measuring the different types of relaxation times, okay, I can measure all three motions using NMR technique itself. Okay, in one technique, depending on the way I vary the applied magnetic field strength, I can measure all the dynamics, different time scales can be captured using this particular technique. And then this is the intro for the why cellular membranes are important and how it is affecting. And one of the membrane protein we study is that rhodopsin. Okay, where is that rhodopsin is present? In our eye. Okay, one of the reason, that is one of the membrane protein which is responsible for night vision purposes. Okay, and all of you would have seen that this rhodopsin protein's function. What is membrane protein? That is what I talked about, is only a membrane. What is membrane protein? Whatever the protein which is embedded within the membrane, little bit is emerging out of the membrane structure. It is the best example is your hair. Hair is, some part is embedded within the skin and some part is away from that. But once I understand the structure and dynamics of this membrane protein, many of the drug industry, 50% of the drugs, okay, whatever they manufacture and allow patients to take it, okay, they derived the functionality based on this one of the well studied membrane protein dynamics. And all the molecular dynamics studies, they need to get experimental information how this dynamics is happening. It is not an easy job with any other technique to happen. What happens whenever light falls on you, immediately its orientation, cis trans conformational change happens. It goes from blind to active region. Not talk too much on that. Okay, that's one of the reasons. That is the relaxation time. Once I know the relaxation time for this nuclei, okay, these nuclei, as I already told you, that these three nuclei will be giving signal at different positions, because their chemical environment is different here, different here, different here. How this dynamics is happening, I can identify independently. How this dynamics is happening independently. That relaxation time, if I measure it as a function of time, temperature, I get the energy required to make this methyl group to rotate it. I'll talk about it during the next session over there, how it is related. That energetics of the functionality of the membrane proteins, it can be estimated using this fundamental technique. And how this is possible, if I have to look into that, and literally whenever we do this experiment in the lab, okay, what we used to go is that cow slaughter place, we used to go and take the eyeball from that cow and make sure that everything is inside the black box. No light should enter. This entire room, our lab is painted with the black paint. Okay, no light should fall on that, including these ones. That's why we used to wear for that lights, red lights. Okay, and all that experiment we have to do it in the dark, and then we insert it in the magnetic field again. In your magnetic field room also, everything should be covered, including whatever the light is blinking here and there, that also should be covered with black tape. Okay, no light should fall on that whenever I am doing that. The moment, I'll show it at the later stage, the moment light falls on that, immediately it goes to the next state. I cannot distinguish these two states. I have to identify it extremely carefully. You have to perform the experiment. That's why not many people will be doing this experiment. And the next point comes over here. Here also have hydrogen. Here also have hydrogen. Here also have hydrogen. How these hydrogens can be separated from rest of the hydrogens? Because more or less the chemical environment is almost same here. Okay, how do I identify? How do I identify these three hydrogens from the rest of the hydrogens? Aromatic ring is always having hydrogens. Okay, that's where it comes in that their spin quantum number of this hydrogen. Okay, what I do, I selectively take out this, I select this hydrogen atom, I replace with heavy water, I make this hydrogen to become deuterium. Whenever I change it from hydrogen to deuterium, the spin quantum number, instead of 1 of what I showed in the beginning, that becomes 1. Okay, then what happens, whenever the spin quantum number becomes 1, that initial 1 energy levels gets split into 3 energy levels. Okay, this is -1, 0, +1. Sorry, +1, 0, -1. But again, quadrupole effect comes into picture. They are not always equally spaced. The quadrupole effect shifts this lower energy level up and this energy level up, but 0 energy level it brings down. Then earlier, if this quadrupole effect is not there, I would have seen same transition from here to here and here to here. I would have got only one signal whenever I record it for whatever the position I want. But now what I am going to get is, we'll get two peaks, which are how much is the reduction is exactly equivalent to how much is the expansion or increase in the energy level. Therefore, instead of getting signal at one particular point, whatever I would have got it, if there is no quadrupole effect, now the same energy level shows one peak here, one peak here. Two peaks I will observe for the same group or for the same hydrogen deuterium atoms. In that, what these are the details associated with that. For the same, I have deuterated entire my lipid chain the way I showed it in the membrane protein CH3 group. Here what I do, here also too many protons are there, but what I do, I change only these hydrogens with deuterium. Okay, and once I have that, whenever I record the NMR spectrum of the deuterium, okay, these transitions are going to happen. And 1 minute. Okay, and then I think one spectrum is missing. What I get it, instead of getting one peak, I get two peaks. Whenever I get two peaks, my measurable quantity is the distance between those two peaks is enough for my experimental results or derivable results. My job is to just measure what is the distance between these two peaks. Okay, I get one peak for every chain. Okay, and that will enable me to characterize how this length of the across the chain length, your relaxation time is differing, how motion is changing. Okay, all of them can be encapsulated, and these are the little more detailed discussions how this orientation is happening and how this orientation is happening to this particular technique. I can always estimate all the finer details, and what I read to measure at all those, from all those measurements, my job is just to measure what is the distance between two peaks what I observed. That can be connected to the what is the angle it is making with respect to the field strength. I can distinguish different types of motions with that. Okay, it just my interest is to understand that different types of motions can be measured in one shot. I can always identify that, and once I measure the distance between this, whatever the SCD parameter we measure it from the distance between those two peaks. Once I know this delta nu q quadrupolar splitting, once I know that, from that I can measure what would be the cross-sectional area of this individual lipid molecule, and I can measure what would be the length of the membrane thickness, that is length of the chain, whenever I put two lipid molecules together. Okay, that is when you are sitting in this way, what is the average area per lipid, I can measure it, and also the membrane thickness, this thickness can be measured, and also what is the average area per lipid also measured. It is not an easy job to measure it using any other technique. Only other technique is small angle X-ray scattering. With that technique, I can measure the thickness, then I assume that area per lipid. There are different theories associated with that. They are extensively done using that technique. Now, during this condition, now I understood that by measuring NMR spectrometer, I can measure the area per lipid and also thickness of the membrane. Now, what would happen if I change the physical parameters, either pressure or temperature? Okay, how much if I apply more pressure on that, how does it change? If I apply more temperature, if I change the temperature of the system, how does it affect? Those parameters can also be measured. That parameters, whenever I can, how do I create pressure on the system in the biological systems? How does it really happen? Okay, there are different ways. Okay, that we perform that kind of an experiment. We use some osmolytes. We started adding osmolite to the system. That creates osmotic pressure. As you could see that the pressure created in the system by adding just different amounts of osmolites, I can increase up to 100 megapascal of pressure can be created. Not only by adding extra pressure, whatever all of you are sitting over there, whatever the water molecules are there between two chairs, if I take out all the water molecules in between also, that creates osmotic pressure. That creates a dehydration pressure. Okay, now water is also sufficiently filled, all of you stay calm. The moment I take out the water molecules, tension is created in the system. That's where our molecular dynamics simulation guys, they try to simulate it, and that creates lot of pressure. Our one of the papers what we published about 10 years back is that just to show that how applying osmotic pressure and applying dehydration pressure, just to take out both are one and the same, we proved it in that particular work. And also some people literally took the membrane and then they started applying like piston type of pressure, hydrostatic pressure. But the effect of hydrostatic pressure decreased the cross-sectional area from here to here only, though they went up to 140 megapascal. But through osmotic pressure, whenever we measured it, okay, we were able to see approximately 20% change in the cross-sectional area using this osmotic pressure as well as dehydration pressure. Once I know that cross-sectional area change with respect to pressure, I can always calculate our famous what that Young's modulus associated with that particular lipid. How does it change for different composition? This is for the one particular type of lipid molecule. For different lipid molecules, how does it happen? I can always measure it. Through that way, this is shown over there. This clearly shows that approximately 20% variation. Once I know this, there are several other properties, how this water molecule is interacting with the next molecule. Okay, and what are the other protrusion forces which are getting affected. All of you, whenever I'm taking out more water molecules between two lines, then you come nearby each other, then you start protruding to the next layer, and he comes over there. There are other osmotic coefficient. Some of the detailed physics measurable parameters can be extracted by measuring this kind of a technique. And after I left that institution, they started applying same concept with membrane protein. I did the basic work only with membrane. I did it. Now they did it with membrane protein. Okay, with rhodopsin, how does it really go from off state to on state? Okay, if I get time, I'll show it in the afternoon session. Okay, how much time I am left? Yes, 10 minutes. Okay, I'll try to wind up and get started with the new one. Okay, then we'll take a break. Now, all of you understood up to this point. I am just trying to give overview. Usually, I avoid giving a lot of equations. Try to give you overview why we need to care about that. Okay. Final details, as I told you earlier, right? This is the spectrum, what we get it. Can you look at that? Whenever I get that only one free induction decay signal, if I do the Fourier transform, okay, that one signal gives these many peaks. You know that the person Fourier transformation, all of us studied long back, and it was invented many decades back. The person who just introduced Fourier transform can be applied to NMR. He himself got the Nobel Prize. Because the advantages of applying good old mathematical technique to the realistic problem, okay, gave him lot of credits. That's where our biology and chemists started using it. Earlier, it was our physicists' idea, and I had an opportunity to visit the person or attended his 90th birthday party in the same University of Arizona who invented this NMR technique. Okay, whatever the researchers or young faculties who are there, it is not just to go out or go to different places to work here. The environment where you live, okay, the culture, work culture, all those things definitely influence your work. Whenever you get opportunity, keep writing to different places. Okay, at one place definitely you will get it. Okay, don't leave any opportunities. Wherever it is available, keep applying. Do your best and go to a new place. Okay, definitely lot more things. Not that you gain lot of physics and other things. The way you look at life itself will change from one end to the other end. Okay, and that opportunity to work with lamp shift, all of you have heard of it in molecular spectroscopy. That was invented in the same university where I went over there. You get to see the people who work in different way. Okay, that what I have to say over there is how why more number of Nobel prizes were awarded to this field. Okay, it is nothing new they did it. Good old method. Yeah, why don't you go and search this book in the library? If somebody tells you that can solve your problem, that's a great achievement. Same thing happened over there. As I told you, how microscopic information can be studied by just inserting a small component so that every C3 position, what is the corresponding value? What is the splitting quadrupolar splitting value I can identify by doing the Fourier transform method. And once we get this kind of a pack, the way we analyze the data is that, okay, 2HNMR only gives residual quadrupolar couplings. It will give the value, and then what I do, I calculate the area under the curve. Okay, I summarize, and then I identify how many groups could have given this much highly intense peak. Otherwise, all of them should have given the same height, right? Why they are different? We why I am showing this one is why whenever in your classroom your teachers would have given you some spectra to analyze that, right? Data analysis through spectrum is also equally important, not only doing it yourself. Okay, that gives lot of information, lot more things to learn from that. And once we identify that same way, and then I think the same information I have given, how exactly it is connected to order parameter. I think that is a quantum or the molecular dynamics studies, they use this order parameter more. That's basically how ordering it has happened, how many these got bent back or whether they are straight enough. Okay, like that I can identify by measuring that. What we did in this particular technique is whenever we are having it, we try to remove more number of waters over there. How did you remove water from that? The simple technique. I did not add more water at all. I took 100 people, I added two molecules of water. One time I did the experiment. Second time I added 5 atoms. I did not do anything great going to yes. Only thing is what my major contribution over there, once you add it, how do you make sure that no water is getting added up or no water is going out of the given sample tube? They were always trying to put it one small cap into that. After doing one complete experiment, water used to get evaporated. They were not getting the repeatable results whenever you do 2 3 times. One small technique, okay, you go and vacuum seal it. No, vacuum seal it. Just take this kind of a tube. Yes, that's where this. No, it doesn't affect. What I added up, they were just trying to close the cap like that. The moment whenever we do temperature dependent experiment, then immediately water used to get evaporated. Then whenever you do second time experiment, they were not getting the same result. What I did, I opened it here. I connected this one to the vacuum chamber. Okay, once it is evacuated, I melted this portion. Whatever water goes, it has to be there within the box itself. Okay, there are simple techniques. That's why don't think that whoever sitting over there, they did great work and other things. Of course, they are great guys, but opportunities and making use of the opportunity, applying your presence of mind at that point. Okay, that one they captured it. Okay, like that. Anything, if I could have, I have done that means definitely all of you can do that. That's what the bottom line trying to tell that. Okay, with that technique, same area and everything is summarized in one slide. And just to give additional info, once I get that one, I can measure the undulations present over there, and intermediate intermembrane distances can be measured, protrusions can be measured, which are dominating at the shorter distances. All these things, dynamics which are happening in the membrane can be extracted. Information can be extracted from that experimental result. Then there is a lot of very helpful reference papers are given over there, and we established the equivalence of those two. And energetics, what is the Young's modulus of that particular lipid can be estimated over there. How does it vary from other place? That's what I moved from physics to biophysics. I was in chemistry lab. Okay, I think the next post lunch you can come back to India. What I did before going to US and what I am doing right now. You can take that. Is it, or shall I continue for some more? You can stop. Okay. After that, in the same way, little more. Whatever the details, technical details. If you have any questions, you can ask any questions related to this right now, so that otherwise I can cover or I can touch upon those concepts in the afternoon session.
Incoming voice call from +91
Yes, please.
99602 03965. Incoming voice call from +91 99642
Yes.
03965. Incoming voice.
Yes. See, highest state and lowest state only comes with the mathematical expression. Okay, since negative term is already associated, whenever spin of plus of state in the interaction, it goes to the lower energy level. Spin minus of takes to the higher energy level. Okay, that's as you can see that whatever the vibration energy level or rotational energy level, I cannot draw that line. Okay, it is still what I can say that ambiguous question only. It is our interpretation of this energy level or this energy. What is your mental state? If I have to say, if you are happy and other things, only with your expression I can say. There is no physical energy levels in any of the systems. In spectroscopy, that's the bottom line. We always tell that. That's whenever that because when you ask me the first question, I thought how physically I can locate it. There is no this energy level, this energy level. Ladder. That's a representation of that. Yeah. Once like first floor, second floor, we don't have. So that's the confusion depending on that how much energy you want to be supplied to move from this orientation to this orientation. That's how the difference only is relevant to us, not that exact location. Like vibration, stretching, okay, bending, symmetric, asymmetric, all those things you have magnetic moment, orientation. With respect to applied magnetic field, how many possible orientations you have? Two energy levels means one is up spin, down spin. Okay, three energy levels means one this way and the other. Beyond that, if you ask me, we have to just say that quantum mechanically, you have to assume that. How come if spin magnetic moment is 5 by 2, then plus 5 by 2, plus 3 by 2, plus of, and then minus of, plus 3 by selection rules. Then what are the possible transitions? Okay, what is delta I should be? Okay, all of you have studied, right? Delta L, delta N, okay, delta ML, delta MS. So state all those things again, probability factor comes into picture. There are a lot more. We are just at the outset, we are giving the overview basically instead of touching upon the parameters. That's why don't think that there is one more floor. Okay, it is whenever the transition is. That's why I cannot. It is hard to identify whenever you are stable. I make you to jump. Then depending on how much you jump, how much energy you lose or absorb, based on that I will measure the energy gap between you two. Okay, I cannot. It is hard to measure your exact position. That's why spectroscopy is always making that you perturb the system. How much you get perturbed indicates me that what is the available state next to you. That way, yeah, that's a fundamental. So, yes, yes. Ah, mm. Yes. Ah, ah. See what happens over there. Whatever the usually the change is very much. I had this conversation with the ASC professor. When they made this statement, I had to interpret or interrupt and tell them that it does change. Okay, but most of the high frequency measurements when they always think that in the next during afternoon session I'll tell that what is the difference between what I did and what regular NMR lab would do. That they go with 500 megahertz, one 900 megahertz, but all my measurements were done at 10 megahertz. Why we have to do it at 10 megahertz whenever we have to study that? What is the importance of that compared to 100 megahertz? Okay, that position chemical shift, I don't think extremely it deviates from one temperature to the motional narrowing will reduce broadening. Yes. Then it drastically changes. What? The diffusion changes, but interaction that can be measured using line width would change. That will very marginally. What in the next slide is only, as you could see, that it is only temperature. I will not talk about the structure. With dynamics, I can talk much. Otherwise, I would not have plotted from 4 Kelvin to 400 Kelvin. How one of the parameters would change. We pay more attention to the dynamics. Dynamics gets affected enormously compared to the structure. Yeah, feels like that's what spectral density. When I talk about molecular dynamics, right? They go with the spectral density. At what frequency exactly you get the minimum? The way your delta E by delta T, your first derivative becomes maximum, right? Same thing here also we get it. Same thing can be. Yes, yes. Spin quantum number becomes zero. Hence, your I is zero means Mi is zero. Hence, it does not give NMR signal. Huh. That's right. That quadrupole concept comes for a nucleus whose spin quantum number is more than half. 1 and above, because our deuterium is spin 1 nucleus. Whenever we are having spin quantum number more than 1, the quadrupole effect comes into picture. For spin of hydrogen spectrum, we don't get. For carbon 13, we don't get. Yeah. No, this is spin quantum number itself is zero, right? Even. That's why your water, why people work with water? Our entire body is consisting of water. Your hydrogen is also there, oxygen is also there. Since oxygen doesn't give NMR signal, I only concentrate on hydrogen. Ah. Ah. Hmm. True. Yes, that's right. Yes. Plus one. Yes, that's right. That at that point you have to think that quadrupole effect will not be there. Okay, quadrupole effect will come into picture. Your energy levels are not equally spaced. The way I showed you, right? Otherwise, I should have got only one peak. Because of the quadrupole effect, I got spin of one. It got split into several peaks. Okay, and this quantum number, all of you nuclear physics, this university is famous from our Ramchandran sir to today, GR. Uh, how do you calculate the quantum numbers, spin quantum numbers? I am writing hydrogen is off for deuterium 1. Okay, some other nucleus 3 by 2. How do we calculate? What is the model used to calculate? This is the question one of the student asked in US when we were delivering the lecture. How do you say this fellow is having 1 by 2, 3 by 2? Shell model. The way electrons take different number of available valence electrons only contribute, right? Same way nucleons also. The same way nuclear shell model comes into picture. The same philosophy applies. 1s2, 2s2, 2p6, the way you write it, here we go with a different model. Okay? Oh, yes, please. Yeah.
So you're speaking about the internal field here. So you said we for higher nucleus, nucleus is ferromagnetic or something, you need not to have external magnetic.
That's right.
But what about the molecular thing you have used here? They will be having hydrogen and all. Obviously, that will also be having some internal magnetic field, right?
No, that is internal magnetic field. Only ferromagnetic systems will be having it.
No, they will be having to larger value. But what about the even normal if you take hydrogen atom? It will be very
That is
negligible.
extremely negligible. That's why we don't even treat it. It is having that. Okay. That's why the second half we concentrate more on. Okay then. Okay, thank you.